Okay, so last week we talked about the Bohr model. This week we're going to talk about the quantum mechanical model. Okay, you probably heard of the term electron cloud. We're going to assume that electrons are continuously moving, and then where the electron cloud is the most dense, where you see the darker areas in that picture, this is going to be the place where the electron is most likely to be found. And we're going to have to start looking at the atom in a three-dimensional viewpoint.
So like Mr. Harfin has said, this connects to the Bohr model that we talked about before. So one of the things that I want to point out to you is that the Bohr model quantized the electron's energy into orbitals or paths, and they were distinct paths. But the quantum mechanical model doesn't use strict paths, it uses probability. But I want you to realize where they're connected. So two of the important vocab words are the principal energy level and the sublevels that they're divided into. So in this diagram to the right here, if I were to imagine that this is the nucleus here, if you notice there's a 1s here, oops, there's a 1s, and that's kind of where that orbital or that energy level would be. And then you see 2s and 2p, and that's there. And you can see these are connected with dotted lines, but this just kind of shows you how this is connected to the Bohr model. So I just wanted you to see where those dotted lines show the connection. And something that's important is that the amount of sublevels that are in a particular energy level matches that energy level's number. So this is written kind of wordy, but what that means is in the first energy level, there's one type of sublevel. In the second energy level, there's two types of sublevels. In the third, there's three, and in the fourth, there's four. And this keeps going. Now, we only currently have discovered elements into the 7p sublevel. So we know that we have electrons in the 7th energy level, but we have yet to find elements that actually are in 7 different sublevels within that energy level. It's a computer model that's projected that there would be 7. So it's mostly in the prediction state now. But for the ones that we know, you'll see that there is that pattern. So the next vocab is the electron orbitals.
Sorry.
That's okay.
So I'm going to take the third vocabulary word, which is the orbital. This is different from the term orbit that you would use in the Bohr model. The term orbital basically means that this is the region of the nucleus where electrons are most likely to be found. Okay, so this is the final piece of the puzzle. So different types of sublevels have different numbers of orbitals. The important rule here, which is actually not on the slide, but I just want you to kind of highlight somewhere, is that an orbital at maximum, no matter what type of sublevel it's in, can only hold 2 electrons, okay? Now, as Mr. Riley said, different energy levels have different numbers of sublevels and different types of sublevels. So the 4 that we're going to talk about are S, P, D, and F. An S sublevel has 1 orbital, and if you use the rule I said before, that orbital can hold 2 electrons, okay? The next sublevel is a P. In a P sublevel, there happens to be 3 orbitals, and each orbital can hold 2. 3 times 2 is going to give you 6. The third sublevel is D. There happen to be 5 orbitals in a D sublevel, and that's going to give you a maximum of 10 electrons in that particular sublevel, okay? And then finally, the fourth one is an F type of sublevel, and as you can guess by the pattern, it's going to go up by 2, so there happens to be 7 orbitals. 7 times 2 gives you a maximum of 14 electrons. Mr. Riley is going to talk about the shapes of these orbitals. Oh, sorry, of these sublevels.
So the different orbitals in each sublevel have shapes. So in the S sublevel, there's 1 orbital and it's shaped like a sphere or a ball. So inside that region of space, there'd be 2 electrons. A P looks like the P sublevel, the shape looks like a dumbbell. And you'll notice that it goes on each of the 3D axes. So you've got the X, the Z, and the Y axes. Since each of those 3 orbitals hold 2 electrons, that's going to give you those 6 electrons. Then you have the D sublevel, which looks like a clover for 4 of them, and the 5th one is complex. And for F, they're all very complex. There's not really a shape that you can relate it to necessarily. I've heard some people refer to them as flowers, but it doesn't fit all of them. And the term Aufbau is German for building up. So it's showing you how the atom is built up. And electrons are added one at a time to the lowest possible energy level that's available. And this is so that the atom is stable. Electrons, just like we do, electrons want to do what they'll put in the least amount of energy in order to find stability. So as the principal energy increases, there actually becomes to be little overlaps between the sublevels when we are looking at how much energy is required. So the increasing energy is on this axis here. And if you notice, the 4s and the 3d are pretty close in terms of energy. What's going to happen is the 4s is going to fill with electrons first, because this atom can become more stable by filling 2 electrons in a 4s sublevel faster than it would have to take 10 electrons to fill that 3d sublevel. So electrons are going to fill as with as little energy as possible in order to find a stable status for that atom. So they're going, the big key here is electrons will fill the lowest energy orbitals first.
The second rule is called the Pauli exclusion principle, and this is going to explain why only 2 electrons can be in any orbital. Remember, electrons are negative, so you can't have a lot of electrons in the same place because like charges will repel each other. So the way we get around this is that each orbital can hold 2, and what we say is that each electron will be having the opposite spin. One's going to spin clockwise, one's going to spin counterclockwise, and the opposing spin cancels the effects, okay? So again, if you look at the picture at the bottom of this page, you're going to see that the blue arrow is pointing north. That's one way. You can kind of see the red arrow, the purple arrow, which is indicating the spin. So one's spinning clockwise, one's spinning counterclockwise. So again, take away 2 electrons in an orbital because you can't have too many negatives repelling each other.
And the final rule is Hund's rule. And it has, again, to do with the fact that electrons repel each other. So since electrons all have a negative charge, they want to be spaced out as much as possible. So even though these 3 electrons are all going into the 2p sublevel, they're going to each be placed in a separate orbital before doubling up. So this top example is correct, where each electron is in a separate orbital, where this bottom example does not do this. So these are not having the electrons as far apart as possible. This is having the electrons as far apart as possible, but still being within that sublevel. And this will create, they're going to fill in the way that creates the most unpaired electrons. And again, that's so those negative charges are as spaced out as possible.
And as we continue on, I think it would be a good idea for you to pause the video for a second. Make sure you get your periodic table out, because for the remaining 5 or 6 slides, it'll be important, okay? So just do that if you can. So if you take a look here at the periodic table here, you will notice that the way that the periodic table is organized actually takes into account all the different sublevels and energy levels that we just were talking about. You probably have wondered why the periodic table looks the way it does, and I think this actually kind of answers it. You can kind of see where each of the different sublevels and energy levels are, and it's also going to help as Ms. O'Reilly goes to the next slide, is she's going to tell us how to build up using Aufbau, so you can kind of see that as you go increasing by atomic number, you're going to go from 1s to 2s to 2p to 3s to 3p. You kind of follow it like a yellow brick road, and she's going to tell you a little bit more about that yellow brick road.
So if I line up the sublevels in this diagram here, it's going to be the yellow brick road. This is referred to sometimes as the diagonal rule. This diagonal rule, what it shows is diagonal arrows, which is where the name comes from. If I list the sublevels in increasing order, so I've got the 1s, the 2s, 2p, 3s, 3p, 3d, and so forth, then I connect them with these arrows pointing downward. What ends up happening is after I finish the first arrow with the 1s, then I would continue where the next arrow starts, where there's 2s. And then it would go to the next arrow, which is 2p and 3s, and so forth. So once you finish one arrow, you continue to the next one. And it would end up looking like this as the final order. That relates to the last slide where you could see it across your periodic table as it goes straight down each row. it's going to match that same pattern as if you listed it this way and did a diagonal rule.
Okay, so this is just going to be a form of practice. This is taking the element calcium. The important thing with your periodic table is that you need to usually count the number of electrons an atom has to be able to correctly identify it or to write its configuration. So I would look at calcium. It's an alkaline earth metal. It's in group 2, and you're going to see that it has 20 protons. Remember from the beginning of the year that if you know the number of protons, you know the number of electrons in a neutral atom. So calcium has 20 protons, which is going to indicate to you that it also has 20 electrons. And this diagram is going to show you that you're going to use the Aufbau principle to build up, which is what the prior slides were showing. And you're going to, if you add up all the arrows, it is going to add up to 20. It's also showing you the opposite spins of the Pauli exclusion. And then it's also, even though it's not an animation that's showing you, it's also obeying Hund's rule also.
So we have some examples for you to try. So I want you to pause your video, compare these to your periodic table, and see if you can figure out, using those rules and that explanation that Mr. Harfness just gave you, and see if you can figure out what's what. And then the Edpuzzle questions will pop up. So now that you've had a chance to try each of these, you should have found that the number 1 is, and I already forgot them, number 1 is nickel. Number 2 is carbon.
Because there's 6.
And number 3 is, I think we said sulfur. Yes, sulfur.
Because there's 16.
Right. And those 2 different rules that you can do is you can follow the yellow brick road and kind of look at it like a map where it lands. So looking at, how many are in the 3D and counting across the area, or you can just simply count the number of arrows to identify it, because each arrow represents those electrons.
Okay, so the important thing about this slide is actually this bottom picture. When you look at the denotation or the notation of a configuration, it tells you a lot about it. When you see the big regular sized numeral or number, it's telling you what energy level is. So that one where the arrow is pointing is saying you're in energy level 1. The letter, whether it's S, T, D, or F, is going to indicate to you which type of sublevel you're in. Okay, so this is saying you're in energy level number 1, and you're in the S sublevel. And you should think to yourself, well, I know that the S sublevel only holds 2 electrons. He says 1 orbital. That last one, that superscript 1, is telling you that there happens to be 1 electron in the 1s orbital, saying to you that you're in energy level 1, etc. Okay, and then configuration, its actual definition is just going to be not only about where the probability of the electron being found, but also the energy that the electron particularly possesses.
And comparing those electron configurations to the orbital diagrams before, you'll notice they have all the same information, almost all the same information. The orbital diagram actually gives you a little bit more information because it tells you the direction of the spin and which particular orbitals the electrons are in. But if you compare these, you notice that for lithium, you have 1s2. So that's the 1s sublevel with 2 arrows or 2 electrons in it. The 2s1, you see the 2s sublevel with 1 arrow for the 1 electron. And that's the same for all of these examples. And you'll also notice, Hund's rule, where it's 1 arrow in each orbital before doubling up, is also are also applied here. Aufbau's principles and Pauli exclusion principle, all 3 rules are being applied for these examples. So the pattern that you're noticing is that they're giving you a very similar description of the number of electrons. And both of these, the electron configuration and orbital diagrams, can be used to identify an element.
Okay, so it's a good idea to pause, and we're going to let you practice one more time. Okay, so again, you're going to follow along and count. I think that the first one, if you add it up, will be sulfur because there are 16 electrons. The second one, there was a lot of electrons. I think it was 82, so it turned out to be lead. And then the third one, there was only 9, and I think it turned out to be fluorine. And we're going to be going a lot deeper into this next week. So this is kind of like your opening act, your little synopsis of what's about to come.